All right, welcome back. So it's a real pleasure to have Alan Heavens from Imperial College. He's going to give us a lecture course on gravitational lensing. But I just wanted to mention that Alan over the years has been working on he has worked on a lot of different topics in cosmology, all the way from peaks theory to lensing to astrostatistics. And I remember as a student, my first introduction to statistics in cosmology was a really excellent set of lecture notes, which you will find on the archive. So just search for Alan Heavens, Cosmology, Statistics. This is the only thing I think that will come up. I encourage you all to take a look. And I'm really looking forward to also his lectures on gravitational lensing. So please.
Thanks, Aseem. So good afternoon, everybody. Can you hear me all right? Yeah. So I've got 4 lectures to give you on gravitational lensing. The topics I've chosen to cover are to start from the beginning and show you how gravitational lensing works within general relativity and indeed within other gravity theories, and show you derive some of the basic results of lensing, but with a particular focus on cosmic shear. So just to give you a little bit of context, we'll look at photon geodesics in general, then look at light bending by point masses, which essentially gives you a Green's function for the light bending by any general distribution of matter. And these are useful for looking at the light bending by individual objects along the line of sight between a source and ourselves. But the problem that we really need to get to grips with is the more general problem of light that has passed through a clumpy universe where it's continuously being bent by gravity. And to do that properly, we can generalize the equations to see how that works. So that gives us the theory of how light gets bent. And then go on to, after that, is to show how you can use that theory to confront observations with theory. What are the observable consequences of the light bending that we can use? And then finally, if there's time, I'll say a little bit about CMB lensing in the last lecture, depending on how much time we have. So let's start. So how many of you have studied general relativity? Is there anybody that's unfamiliar with? Okay, that's pretty much everybody. Anybody unfamiliar with relativity, general relativity? Okay, good. Just to start at the very beginning, if we recall one of the principles of relativity, which is that is the equivalence principle, which is that in a locally inertial frame, we have special relativity. So if you recall special relativity lectures, then you know that if you have a freely moving particle, like collapse space-time to two dimensions, then the world line of a freely moving particle is going to be a straight line, which should be at no more than 45 degrees away from the CT axis. So we can parameterize the world line by a set of coordinates, psi mu, which depends on, say, the proper time of the particle, and psi mu here in a Cartesian system would just be CT and X, for example. And the equation of this line, and you can show with a couple of lines of algebra, is that d2 psi mu by d tau squared is 0. So these are parameterized solutions for t and x, for time and space, as a function of this of the proper time that increases along the world line. So this applies in a locally inertial frame. If we transform this to a more general frame where we have some more general coordinates. Say x mu is a function of tau for a massive particle. Then we get the famous geodesic equation. Which I guess you've all seen before. Now, if we can generalize this, this doesn't have to be the proper time, and it's more useful for photons, for which the proper time is zeroed, to make this more general. And just have a parameter p, which increases, or if you're obtuse, decreases along the world line in a monotonic fashion. Okay, so we'll be using this to look at light bending by individual objects, but also through the universe as a whole. The gamma here is the affine connection. So for a given metric tensor, then we can write the affine connection in terms of the metric and its derivatives. As follows. So for a given metric, you can then work out the trajectories of photons or massive particles in the metric. And just to remind you that this is when the indices are at the top, then this is defined as the inverse of the metric tensor in that way. So in these lectures, I'm not going to derive any of the metrics. We'll deal with the Schwarzschild metric or a point mass, and we'll also deal with the metric of a slightly perturbed universe. I'm not going to derive those. Those are in the half of general relativity, which is the matter tells space how to curve bit, which I'm not going to cover at all. So I'll just take the metrics as being given, and we'll work out the orbits in those metrics. So for example, if we have the Schwarzschild metric, then in the usual polar coordinates, then the Schwarzschild metric can be written in this form, where t is the time which would be recorded at a stationary observer at infinity. R here is an angular diameter distance as determined from the center. ds squared is the interval. So just to remind you that this, you can then read off the metric tensor just from the components of the that are in the interval here. So there are no cross terms that couple dr and dt, for example, so all of the off-diagonal elements are 0, and the diagonal elements are just come from reading off the coefficients, and alpha here depends on the mass and the radius in that way. So here, we use spherical polars and t as the coordinates. Okay, so by doing a lot of work, you can calculate all of these coefficients and work out the equations of motion. What I want to introduce you to, if you haven't seen it before, is a variational method which allows you to compute the equations of motion much more quickly when you have metrics of which have a lot of symmetry, and there's an enormous amount of symmetry, obviously, in this example. Otherwise, what you tend to do is there's an enormous number of summations here, and you find that almost all of these terms end up being 0 with in symmetric metrics. So an alternative is to note that we'll do this for a massive particle and then generalize to a photon, is that along the world line, then the proper time is maximized. So if we have some world line that has fixed endpoints at A and B, say, then the proper time, or c times the proper time, integrated along the path is stationary. So we can write this in terms of a Lagrangian which depends on the position and the force velocity. And that quantity is stationary. And L squared is c squared times dt by dp squared, which is just ds by dp squared, which we can write as g mu nu times x dot mu x dot nu. Okay, so given that this is stationary, then L has to obey the Euler-Lagrange equations. Is everybody familiar with these? Is anybody unfamiliar? If you are, then just catch me at the end and I can give you a reference. So for each of the mu's, then the Lagrangian has to obey this equation. So the dot here is d by dp. So this is very useful because it basically what this is equivalent to the geodesic equation, but it means that you don't have to calculate an enormous number of those affine connections to do it. It doesn't help if there's no symmetry in the problem. You'll end up doing a a lot of work, or probably the same amount of work. But if there is a great deal of symmetry in the problem, then this is a very rapid way of getting the equations of motion. Just to say that because L involves the square root of this thing, it's convenient often to work with L squared. So if you write down the equivalent expression for L squared rather than L, then you'll immediately recognize that there's going to be one extra term that comes in here when you differentiate this. You'll have a 2L times dl by dx dot mu. And the differentiation of the L gives an extra term which we need to consider. It's minus 2 dl by dp times dl by dx dot mu. However, at the moment, p is just some arbitrary parameter that increases along the world line, but we can make a specific choice or restrict it to a particular set of parameters called affine parameters. Where dl by dp is equal to 0. So you can always do this, and that makes things just a bit more convenient because you no longer have any square root in that appears if you look at L. So it doesn't really matter how we parameterize this curve, because in the end, what you end up with is 4 parametric solutions for the 4 space-time coordinates in terms of the parameter, and you would then typically eliminate the parameter to get the spatial positions as a function of time, typically. So it doesn't really matter too much what this parameter is. It's going to be eliminated in the end. So this derivation breaks if you apply it to photons, but the equations in the end end up being the same for photons. And we can use that to look at the geodesics for light. So let's have a look as an example at the Schwarzschild metric. So the first thing is to write down what the Lagrangian is, which we can just read off from here. Essentially, we just replace the dt by t dot, dr by r dot, and so on. So that's L squared, which is a function of the coordinates and the derivatives, the x dots. So if we think about the symmetry of this problem, we're going to consider light being bent by some mass, and by the symmetry we can choose that, well, that orbit is going to be in a plane, so there'll be nothing to break that, no symmetry that could take it out of a plane. So we can define the orbit for convenience. to be the equatorial plane in the polar coordinates, and then we lose the theta dot terms, and sine theta becomes 1. Okay, now we see that, that the equations lead to some conserved quantities. You'll see that there's no explicit dependence of L squared on T, or indeed on phi. So it's a stationary metric, there's no time dependence. There's some R dependence through alpha, there's an R that appears here, but T and phi, there's no explicit dependence on T and phi. So if we look at the first of the Euler-Lagrange equations where mu is equal to 0, then this term disappears, and we have a conserved quantity. So as very often appears in physics, symmetries in the problem lead to conserved quantities. So from this first term, dl squared by dt dot, we find that alpha times t dot is equal to a constant. Which is effectively a conservation of energy. And similarly, if we apply the Euler-Lagrange equation to x mu, where x mu is phi, there's no phi dependence of L squared, so we get a conserved quantity which is dl squared by d phi dot. Which, remembering that we've chosen sine theta to be 1, tells us that r squared times phi dot is a constant, which expresses conservation of angular momentum. So we have these two conserved quantities that come from the symmetry of the metric. Okay, so far, any questions? Okay. So let's have a look at the equation of motion. There's a couple of ways to do this. We could evidently apply the Euler-Lagrange equations to the case when x mu is equal to r. So that's slightly complicated because there is an r dependence in the equation, in the Lagrangian, through alpha and through the r that appears. So a trick we can use is that for photons, we have L squared is equal to 0. So it's following null GD6. So we can then write an equation for r dot using the fact that we now know something about t dot and phi dot from their conserved quantities. So if we simply rearrange the equation here for r dot with L squared is equal to 0, and losing this term and losing the sine squared theta, then we end up with this, which we can then write in terms of the conserved quantities. Alpha times t dot is just k squared. And this one we can write as r squared phi dot squared is h squared over r squared. Okay, so for a given orbit where we know the conserved quantities k and h, then we could work out r as a function of the parameter p and find the orbit in that way. So what we're interested in here is not so much the time dependence of this thing. So we're not interested in we might be, but in this case we're not interested in how the radius depends on time. But the case that we want to consider is light bending by an object. So we're actually interested in how r depends on the angles. So we can eliminate time from this to get r as a function of phi, or it turns out to be more convenient to determine 1 over r as a function of time, as a function of angle. So if we let u be 1 over r, so we want r as a function of phi or u as a function of phi, we can calculate du by d phi from the fact that that is 1 over r squared minus 1 over r squared dr by d phi, which is minus 1 over r squared times r dot divided by phi dot. And you'll notice that then we have r squared times phi dot, which is just h. Okay, so that's just simply minus r dot divided by the specific angular momentum of the orbit. So h looks just like the ordinary Newtonian angular momentum per unit mass, r squared times a frequency, but just be aware that r is defined differently from ordinary Newtonian physics, or it can be different in curved space-time. The time coordinate is different as well, so it has a superficial similarity, but there are some slight differences. Okay, let's proceed though. If we multiply by h and square it, then h squared du by d phi squared is r dot squared, which is what we had before. So we can write this 1 over r squared as u squared, and alpha is now a function of u. So if we differentiate this, we can get an equation of motion, if you like. So this term disappears. There are two terms that come from this. And an h squared. So since alpha is equal to 1 minus 2 gm over c squared times u. So if we multiply that out and differentiate and divide by 2, then you get this. So if we divide by h squared, we get this very simple equation for the orbit I think I maybe have the signs wrong here, sorry. Yeah. We end up with this extremely simple equation for the orbit, and this is exact. So there's no approximations been done here. So now we can make some approximations if this term is small. So if the mass is relatively small, then we can do this as a perturbed solution. So if we write it in terms of an unperturbed solution where m is 0 and then a small perturbation u1, then we have to solve this equation, which I expect you've seen before somewhere. So we know the solutions to the harmonic equation. And this is the equation of a straight line, even though it perhaps doesn't look like it. So we can choose the origin of phi to remove one or other of the terms if we wish. And the solution is a straight line. U naught is equal to sine phi over r. So it's clearly a straight line with r sine phi being a constant. So the unperturbed solution, as we would expect, is just a straight line trajectory like this. Okay, so let's have a look at the perturbation now. So if we take the general equation and subtract off the zero order unperturbed solution, then we just get left with the equation for U1. And we'll approximate this by the U squared on the right-hand side will replaced by the unperturbed solution U naught. Okay, so now we have another equation which you can also solve. You need to find the particular integral. The complementary function is obviously going to give you the same solution as u0, so that doesn't tell us anything new. So the new term comes from the particular integral, which you can find by usual techniques. So let me just give you the solution. As usual with the sine squared, you would write this in terms of the double angle, and then find a harmonic solution, which is a combination of sine 2 phi and cos 2 phi terms in the usual way, and a constant as well. Yeah, when you write this as a double angle formula, you'll end up with a constant and a cos 2 phi, I think, term comes in. So the particular integral is a constant plus a combination of sines and cosines of 2 phi. So let me just give you the solution. As follows. Okay, so that's the perturbed solution. It's not exact because only in this last step, when we've replaced u squared by u0 squared, then we've made an approximation here. So this is not exact. But it's fine unless you're going relatively close to a black hole or something, which we're not concerned with here. Okay, so let's just explore this solution a little bit. So we have the mass here. The unperturbed trajectory is here. And the perturbed solution actually bends away on both sides, heading asymptotically to an angle that is not 0 and not pi at the other end. So if we look on this side here, when r tends to infinity, so when u tends to 0, the angle here, which is the way I've defined it, that angle would be minus phi. Let's call that minus phi minus infinity. So this angle is pretty small in practical cases, so we can make a small angle approximation. So when u goes to 0 and sine phi is approximately phi, cos 2 phi is approximately 1, this order. So we find that phi is, when you solve that, is minus 2gm over c squared r. Just to remind you that that's so the impact parameter, or the point of closest approach here is r. Okay, so we find that we have the trajectory tends to a non-zero angle at this side, and then by symmetry, or more formally if you like, you can find that the solution at the other end is that pi at plus infinity is pi plus the same angle. Okay. So it's spent So the photon is bent through an angle alpha. Let me call it alpha tilde because I had an alpha before. It's bent through by an angle 4 GM over RC squared, the famous result that Einstein got at the second attempt. So I'm not going to do it, but you can do a Newtonian type calculation as well. And as you probably know, I'm sure you do know that if you do that, you essentially assign the particle, the photon, a mass, make it E over c squared if you like, and you ignore relativity and you allow its speed to change, and just treat it as a classical trajectory problem. If you use Newtonian physics, then the answer that you get is precisely half this. And so the reason for the source of the extra factor of 2, if you go back to it, it comes from, I think I've rubbed it off now, but if you go back to the to the metric, then you have 2 perturbing terms, one in the time component and the other one in the spatial curvature component. You have the 1 over alpha term, and it's that 1 over alpha term which gives you that extra factor of 2. So it's the curvature of space which gives you the extra factor of 2 in the light bending. So as you're aware, that the difference between these 2 calculations allows a test which was famously done in 1919 by Eddington's experiment to Sobral and Principe off the coast of Africa. And so this is one of the original plates. And you can see, well, you probably can't, but you can see where there's a couple of stars which are marked here. So this is the sun obscured by the eclipse, so that you can see the stars behind. By comparing measurements of the positions of the stars before and after the passage of the sun in front, you can make the calculations. So I've been setting this as a problem because it's the centenary of this experiment. I've been giving my students this problem to solve as a statistics problem, and you can get the original data freely available from the Royal Society website. You can find the original paper, download the data, and do a statistical analysis of this. It's quite an interesting stats problem. It's not quite trivial because you measure what you do is to take 2 plates, one taken with the sun a long way away and another with the sun almost in the way, and you measure the differences, so you measure the displacements. And it's a slightly interesting statistics problem because actually what you measure has a lot of nuisance parameters in it, because you've essentially got to take these 2 plates, put them on top of each other, and measure displacement. So there's a measurement error, but there's also errors that come from putting the plates on top of each other. They may not be quite registered properly, so they may be offset, and they may be rotated, and they may have expanded or contracted because of temperature variations or moisture that have been absorbed. So there's a lot of nuisance parameters. There's about 7, I think, nuisance parameters that involve in doing the statistical analysis, which you need to marginalize out. No doubt Ben Van Dalt will talk to you towards the end of the course about how you do this sort of thing, properly. It's also quite a challenging experiment because the displacements are extremely small. As you probably know, at the limb of the arc of the sun, the bend angle is around about 1.75 arc seconds for GR. The ones further away are smaller by a factor of scaling like 1 over r. So this is an image with the original data showing the displacements, but the displacements have been magnified by, I think, a factor of 50, so you can see them. So it's a fairly challenging thing to do, but they did it successfully and got more or less the right answer, more or less subject of some debate still. Okay, so you can then use this as a Green's function for analyzing the bending of light by individual objects. And it is used in cosmology. It's a difficult thing to do. Oh, I should say, yes, when the results came back from the expedition showing that the results favored Einstein over Newton, Einstein was was very tickled by this and wrote a postcard to his mother. This is his postcard. It's written in German, so I'll translate it for you. It says, Liebe Mutter, dear mother. Unfortunately, I don't speak German, so that's all I can read. But so we can use this as a Green's function to work out the vectorial bend angle on the sky for any collection of mass as a single foreground lensing object. And so that can be used, for example, with galaxy clusters. So here you can see some, it's not come out so well, but there's some arcs that you can see around this galaxy cluster where the positions of the galaxies have been moved, and some of them have been highly distorted. So I'll talk tomorrow about the distortions of the images that we get from lensing, which is the main signal that we use for looking at lensing on a very wide angular scale. But in these examples where you have very strong lensing events, the images get distorted a lot, and you can probably just about make out some of these very long, thin images. They're not very long, thin galaxies, but they're images that have been stretched out by the light bending. So if you have a good mass model for the foreground object, then you can use this for cosmology. So I'll perhaps just say one or two things informally about it. Is that if you have a foreground object with a distant galaxy, then the light gets bent through this angle, alpha tilde. So if you took this result and then integrated over a certain mass distribution, then various things happen. Firstly, the position of the image gets changed, and that gets changed in a cosmology-dependent way, because if you do some simple geometry, if this is the source here, this is the image here, and the lens is here, and if this angle is phi, source rather, an image, that, let me start again and make this bigger. So this angle is also alpha. And these angles are typically very small, round about an arc-second bending angle for a large galaxy, round about an arc-minute for a large cluster of galaxies. So these are particularly all small angles. So if we call this angle phi and this angle theta, then the distance measurement that we need to consider is the angular diameter distance, which is defined such that this transverse distance of the image with respect to the lens is, in terms of the angular diameter distance, is ds times theta. Okay, so that's the distance measurement we need to have in curved space. That's not going to be the same as the ruler distance that you would measure by trotting along this axis. And that is equal to this distance here, which is ds times phi from this thin triangle, plus this distance, which from this triangle here is the angular diameter distance from the lens to the source, times the bending angle. Okay, so there's cosmological information in there because typically we would have redshifts for the source, redshifts for the lens, and the translation between the redshift and the angular diameter distance depends on cosmology. Okay, so in principle, there is information there in the cosmology by looking at the displacements and so on. And if you've got a decent mass model for the object which is doing the lensing, then in principle you can do cosmology with it. But it's challenging because you need to have a good model for the mass, and that makes it quite challenging. So most of the focus on using gravitational lensing for doing cosmology is not in this strong lensing regime, but more in terms of the very small distortions that you get by looking at objects on the over essentially a large fraction of the sky. So that requires a bit more development of the theory to work out what the theoretical properties of the distortions would be for light which has passed through a clumpy universe all the way along. So quite often people take shortcuts at this point and say, we'll essentially model the distortion of a background image by a whole sequence of these small deflections, and that really doesn't work terribly well. But I'll show you tomorrow how you can do this and calculate in a continuous way what the distortion is due to lensing by the general distribution of matter. I won't start that now because we've only got a few minutes left, so I think what I'll do is to finish a little bit early and start that tomorrow. But, are there any questions on this part? Hopefully many of you have seen this bit before, but I suspect that tomorrow's will be new to most of you.